Hello and welcome back. And the second set of lectures will deal with sets of real numbers. So this would be open, closed, and certain special classes of sets, which will be the crux of what we are going to study later on. And this lecture and henceforward will assume the definition of interval and its basic property. Do you guys really know the definition of interval? Try. So what's the open set? An open set, a set Z of real numbers is said to be open if for each x belonging to Z there exists a positive number epsilon such that any real number y with the property mod of x minus y less than epsilon is in Z. In other words, if Z is open, then for each and every element x in Z and for each epsilon greater than 0, the real number y with this property that distance between x and y is less than epsilon, then y will always be in Z. If you think it over, then what does it say? This simply says that y lies between x minus epsilon, comma x plus epsilon. So for each x, consider an open interval x minus epsilon, comma x plus epsilon. And we are saying that Z is open means that open interval x minus epsilon, x plus epsilon is going to be a subset of Z. Think about it. So that's what the alternative definition. Z is open if for every x in Z there exists an open interval I such that x is in I which is completely inside Z. Open intervals are open set. Try to verify using the definition. Empty set, there's nothing to verify. The set of real numbers, these are open. The following proposition describes two important characteristics of classes of open sets. The intersection of finite number of open sets is open. The union of arbitrary collection of open sets is open. So given any number of open sets, you can only take finite number of intersections. On the other hand, you can take arbitrary union. Let's start with the proof. So in the intersection case, it's enough to prove for two open sets, say Z1 and Z2. My question is why? Anyway, once you're confident that only two open sets will be enough for the proof, we begin the proof. If Z1 intersection Z2 is empty, then obviously empty set is open, so we have nothing to prove. So we'll assume that not empty intersection, and hence let x be in Z1 intersection Z2. Since Z1 is open, x belongs to Z1, you'll find some epsilon 1 greater than 0 such that all y with this property are in Z1 and so on for epsilon 2. For all y satisfying this property are in Z2. So of this epsilon 1 and epsilon 2, both are positive, take epsilon to be minimum of epsilon 1 and epsilon 2. Again, epsilon is positive, and again all y satisfying this property is going to be both in Z1 and Z2. That means y belongs to Z1 and Z2, and by definition Z1 intersection Z2 is open. Second case is quite trivial to prove. G is the union of an arbitrary class script Z of open sets. And x belongs to Z, then x belongs to one of the member, say Z lambda. Z lambda being open for some positive number epsilon. In fact, for all positive number epsilon, we have that all y with this property are in Zy, hence in Z, because of the Z's union of Z lambdas. This proves Z is open. Now, why arbitrary intersection is not good enough? Here is an example. Consider Z and these are open sets, and then take intersection of this family of open sets. What you observe is the singleton set 0, which is not open. Why? So we know that the definition of open sets, finite intersection of open set is open, and arbitrary union of open set is open. Next, very important characterization of structure of open sets in R. Remember, this is not true for any arbitrary open sets, which you may have learned in topology or may not. But open sets of R, this particular property. Every open set of real numbers is the union of countable collection of disjoint open intervals. So any open set can be written as countable union of disjoint open intervals. Proof. Let G be an open set. If G is empty, nothing to prove. So let G be non-empty. For each x belonging to Z, there exists an open interval I such that x belongs to I, which in turn is a subset of Z. That's we have already seen. Now, let us consider Ix to be the union of all such I. Now, what can you tell about Ix? Clearly, Ix is open, union of open intervals, and it's a subset of Z. That's our first observation. Ix contains every open interval which contains X and is contained in Z. In other words, Ix is the largest open set containing X and which is contained in Z. So in some sense, Ix is the largest. Okay. Third and important, if J is under pointed Ix, then Iz is Ix. Well, I'm leaving this to you. So now, script I be the class of all such distinct interval Ix for point X in Z. So collect all such distinct interval Ix for points X. For each X, we just collect one Ix. And then you'll have all sorts of Ix, but obviously you can see that some of these Ix are same. So we need only distinct. Observation 1 allows us to conclude that Z, which is defined as union of all these Ix, is in fact Z equals to this union. Further, the members of I are disjoint because if Ix and Y are two members, they are not disjoint. Say Z belongs to Ix, then Z belongs to both Ix and Z belongs to both Iy, and from third observation, they have to be equal, contradicting the distinctness of members of I. So now we only need to show that this collection is countable. Let ZR denote the set of rational points in Z. Clearly, ZR is non-empty. Define a map F from ZR to I by associating R with unique interval in IR, in I which contains R. Obviously, we can do that. F is onto Y. Furthermore, since ZR is countable, I is also going to be countable because of the fact that F is countable. This completes the proof. Well, what is important and in fact interesting is this proposition, which says that if C Scripts in fact be a collection of open subsets of real numbers. Then inevitably you'll find a subcollection, countable subcollection Zi of C. Says that union of Z is equals to union of Zi's. So prove this statement. This is the only exercise for it. But before stopping, let us give some time to compare the propositions. The previous proposition says that every open set is union of countable collection of this is an open interval. And this says that CB is any collection of open subsets. And in fact, this collection is somehow similar to some arbitrary subcollection, countable subcollection Zi. Think hard. See you soon.